Okay. I'll save the notes, all right? All right, so that's basically how you do something about the y-axis, okay? As you follow this method right here. Now, this can get tricky. There are some, hey guys in the back, zip it, okay? This can get tricky because it could depend upon what exactly we're trying to spin. In this particular case, it was fine because the area in question was bound both by the y-axis and the x-axis, so it didn't matter how I looked at things. But in this next example we're going to look at, things can get, you're going to see it gets a little trickier. So we're going to do, with this example here, we're going to do the area bound by x squared.
So this is the general one?
From 0 to 2. From 0 to 2, excuse me. Bound by the x squared from 0 to 2, spun about the y-axis. Okay? So in this particular problem here, the area underneath x squared from 0 to 2 is that zone right there. Okay? But we're now spinning it about the y-axis that way. Okay?
Does that do anything to it?
It will, because if I were to do this in terms of the y-axis, when I rewrite my integral, it's not going to give me this stuff in black here. It's going to give me the stuff in blue instead. Okay? It will give me that area. And that's not the area I want. I want the area in black spun, not the area in blue spun. Okay? So it means I'm going to have to kind of rethink my integral when I convert it to y. Okay, to do a revolution about y. Okay? For example, easy part would be finding limits of integration. That's going to be 0 right here. And this point up here is going to be 2 what? 4. Okay? So my limits of integration will be from 0 to 4. No problem there. Okay? But when I want the black area, so what do I have to do? I still have to find the stuff in blue, but I'm going to have to subtract it from the total area. So really, I've got two curves here now that I have to deal with. This box here, that's formed by the line x equals 2, okay? And then our curve here, which is going to be in terms of y, whatever x squared is in terms of y. By the way, it's square root of y. That's what it would become. X equals the square root of y is the same as x squared. As a function of y. So that's going to be what we're going to do. So we're going to set up this integral then as the integral from 0 to 4 of pi times 2 squared minus root y squared dy. Okay, and that's how we're going to find the area in black.
Why are you doing root y?
I'm sorry?
Why are you doing root y?
Root y? Our function is x squared, y equals x squared. To convert that into a function of y, it'd be plus or minus y equals x, and because we're dealing with the positive side of the y-axis, we choose the positive root. If we're down on the negative side of the y-axis, we take the negative root. Not that's going to make a difference in our problem. Okay. So that would be our integral. If we work that out, we would get the answer here.
Oh, you're doing f of x minus g.
Exactly.
Okay.
This is turned into a two-function problem. This actually becomes a washer method now. Okay? Now, what was the problem with this? It became a phenomenal what to do? Pain in the rear end, right? Because the area in question was the wrong area. We had to completely rethink the problem. Okay? And if you didn't catch that, this thing could have gone straight. There ends up being a better way of doing something like this. Yes?
Where did 2 squared come from?
2 squared, as I was explaining, the area in black is what we wanted.
Right.
Okay? And that's capped off by x equals 2 on this end.
Yeah.
Okay? Well, when I switch it over to y, the function root y is going to be the stuff that's in blue here, not the stuff in black. And since we wanted the stuff in black instead, we had to set this up with a second function. And so that's where we use the upper limit
Okay.
It's sort of the same way when we were doing,
Oh, when it wasn't on the x-axis.
right, it was on the x-axis and we had, you know, we had to cap off the bottom of it or the top of it.
Okay.
Same exact thing there. Yes?
So basically the 2 square represents the area of the whole cube.
Whole box.
Whole box.
And we're subtracting from it the stuff in blue.
Okay.
Okay? And then you, at this point, the answer ends up being 8 pi, where you actually work this thing out. That integral is easy enough to work out. You clean it up, work it out by hand, or use your calculator, because remember, pretty much these are always calculator problems.
And how do you know that it's minus root y? Like how do you know that that root y represents the blue part and not the
Okay, our curve was x squared.
right?
Okay, that's the curved line right here. Okay, the stuff between the curved line and the y would be what's contained by root y. Okay,
Right.
and so that's this zone right here,
Is that
and that's what we did not want. We wanted to get rid of that.
is that something that you just know that?
Well, remember, the integral is always going to give you the area bound by the curve and the axis. Okay,
Oh.
so when we switch things over to y, the area the area bound by root y and the axis became the stuff in blue, not the stuff in black. The stuff in black was done by the curve and the x-axis.
Oh, we with the blue though, right?
No, we want the black actually, which is why we're doing this double thing
Even
right
when
here.
it's spun around the y-axis?
Yes, because the original area in question was the area in black. That's what we're spinning about y. Okay, and that's why you've got to read these questions very carefully and see exactly what they're asking for.
Oh, okay, we're spinning the black part around the y-axis.
Right, which is why we had to end up with this integral right there. Okay, had we just been spinning the blue part about the y-axis, it'd be easy. This would be exactly like the previous problem. You just integrate.
And how do you know which,
It's on top.
which side we're doing? Or how do you know which part we're doing? How would I be able to know, whether to find the area using the blue part or the black part?
Oh, it's generally given to you in the problem.
Okay.
They never have it.
Like
In this
what-
particular problem, I'm the one who made it up. So I said at the very beginning when we were explaining it, we want the black. Okay. But when we set up the problem, we're getting the blue. Yeah, a typical AP problem like this will probably have this graph for you and the area in question shaded. Okay. And then you would see, okay, from there. All right. That's what happens a lot of the time with these things. Okay. Otherwise, it'll make them quite this difficult. Okay. But also, too, this is a pain in the butt. You have to convert everything into y and then refigure out the system. There's an easier way to do this. Okay. And it's actually, if we're doing a revolution about y with an area like this in the black, the better way to do this is using a completely different method altogether called the shell method. Okay? The shell method is a different way of doing volumes. Okay? And it's one that specifically works for vertical systems, like this one. Okay? Basically how the shell method works, and I'm going to use some props here, okay, is basically it works by layering lateral surface areas one on top of another. So you think of it like this piece of paper here, okay? If I turn it on end and make a little ring here, that shape is a cylinder, and what I've got here, it's hollow in the center, but the cylinder here, that's the lateral surface area of the cylinder, right? The piece of paper is, okay? Well, what I'm doing here with the shell method is I'm taking multiple of these things, adding them one on top of another, okay, to make a thick solid instead. So if I did it with a piece of paper, I'd get this thick ring instead, okay? And now it's a solid, we've got some mass there, done by just nesting one surface area on top of another. So if I pull it out here, there's a single surface area that I take a bunch of them, add them together to make a solid. Okay, does that make sense of what we're doing there? Okay, sort of the same way with the disk method, we're taking 2D disks and adding one on top of another to make a solid. Here we're taking lateral surface areas, adding them one on top of another to make a solid. Okay, so it's working under the same principle. It's just using a different part of the cylinder. So with the disk method, we use the top of the cylinder. Here we're going to use the side of the cylinder. Okay. So what's the formula for lateral surface area? Does anybody remember?
It's circumference times length, or
Height.
height.
Good. Circumference times height. So circumference is 2 pi r times the height. Okay? Well, in our system here, we're going to do the same one we did before. Okay? This is x squared from 0 to 2. Okay? And we're spinning about the y-axis. Okay? To create basically using the shell method, r is going to be a radius. In this case, r is going to be what distance?
2.
Not 2. Oh, okay, 2, yes, the total distance, right. But basically, it's going to be the x, right? The x down here. Okay? And the height is going to be what?
Height 4.
Hey, it's not 4. What's 4?
That's the height.
Okay? If x is 2, y is 4.
Oh,
So what's it going to be here? Y. What's another word for y?
height.
F of x. Okay? So, just like before, where we did it with disks, and we integrated it because we had a lot of different disks, we have a lot of different shells, because remember, we're going to generate this thing by adding up each shell here being spun around. So,
Would this be FY?
I'm sorry?
Would it be FY?
Nope.
Okay.
And that's the beauty of it, is that it's still f of x here. We don't have to do any conversions. But we're going to have several of these that we're going to add in. We're going to have one down here, we're going to have one down there, all throughout the system. What do we use to add a bunch of things together?
Addition.
Well, yes, but in calculus,
Integral.
the integral. Okay? And so we're going to integrate
I like the thinking.
2 pi, r is x, h is f of x. This integral right here, from wherever we start to wherever we end, this here is equal to volume via shell method. Okay? So instead of spinning things around this way, like wood on a lathe, we're spinning it around this way like a pottery wheel. Okay?
It is not f of x. If it's not x squared, it's just.
Nope, it's just f of x. Okay? Because we get this thing to be a three-dimensional, or how we get the x squared involved,
Okay.
is we've got the extra x thrown in there. It's x times f of
And
x.
this
Okay.
works for only the y-axis, correct?
Yeah, we're going to spin this around the y-axis. So it works strictly for vertical systems.
Okay.
Okay, like this one. Alright? We would never, you could do this using the x-axis, but it completely changes the problem, and we don't want it. Okay, we want it like, just like this, okay? We could also do it for another vertical line, so we could say, spin it around the line, x equals -1. And it just adjusts things accordingly. And we can look at that one later.
And then, so are we going to talk about how the function is not on the x-axis?
Oh, so if it's like up here
Yeah.
and not touching, it won't matter with the way this thing gets spun.
Oh, right.
Because we're not doing the zone in between, we're now doing this as a ring instead.
So say it's further out.
Yeah.
Would that make a difference either?
Won't make it, if it's further out, it makes a difference, it just makes your ring bigger though.
Okay.
The math though would still work exactly the same.
Okay. So you don't have to edit the map.
We don't really have to worry too much about, adjustments. In fact, when you do make adjustments, so like say if I did this about a different line here, the thing I would change is actually these limits of integration.
Okay.
These would stay the same. I would just push them out further to the left or right. Okay. So via the shell method, so to set this one up using x squared, it would be the integral from 0 to 2 of 2 pi times x times f of x, which is x squared, dx. We work all that through. The integral from 0 to 2 of x cubed dx. If we work this thing out, that's an easy enough integral to work out. Ends up equaling 8 pi units cubed. That was actually the same answer we would have gotten had we worked this one out completely. Okay? Because we're actually generating the same shape. We're just doing it in two different methods. Okay? The first way we're doing it with disks, so taking disks and layering them one on top of another like so. This one, we're layering things out that way, basically, vertically.
And it's a y-axis?
Wait, why is it x?
What's x times x squared?
Oh.
Okay. All right, and so that's how the shell method. Shell method's actually pretty easy to use. So there's nothing too difficult about it. Okay. This would be a typical shell method problem. Okay.
How would we know when to use it?
It's all based off of what
If it's bound by the, or like.
if we're doing a spinning about the x-axis or about the y-axis.
So y-axis will always use a shell method?
Not always, but for the most part, yes. Unless otherwise stated, just assume it's a shell method.
Oh,
Okay.
okay.
Let's put it this way: the A/B test typically does not do the dis method as a function of y. Okay. If they do, they literally say as a function of y instead. Okay. They'll give you the function of y. Okay. This is how this works. Okay. Again, like I said, variations on it could be if I had like a different horizontal, different vertical line. I just adjust left and right. Not hard to do. Okay. In fact, it usually just happens with these up there. Okay. Any questions?
Yes, sir.
All good.
But how'd you get the A product? You did x to the 4 to the 4 evaluated from 0 to 0?
Yeah. Okay. You can actually plug this in the calculator and work it out. So it's up to you. Okay. All right. Your AP question tonight. That's your homework. Is an AP question. Okay. It's going to ask you basically to do revolution. It's going to find a regular area. Okay. This is going to tell you to take that area, spin about the x-axis as dis method. The question after it says spin it about the line x equals 3 or something like that, which means you're actually doing a shell method. Okay, and you're just adjusting accordingly. All right.
You have to
We did a
adjust.
shell method.
Was it if it's above, you have to subtract, and if it's below, you have to add?
Well, that's for dis method.
For dis.
Here, you're just worrying about A to B here. Okay? And it won't actually, in this particular problem, it says spin about the line x equals 3. The system is bound between, I think, if I remember correctly, it's bound between 0 and 3 anyway. And so it's just a matter of understanding how this spinning works. It's really not a big deal. Okay, it works out fairly straightforward. Yep.
And you said we want to encounter when it's having us spin it about something
Hey,
that
William.
goes through the actual area.
Yeah, we're gonna count.
Big game tonight.
Okay.
it is.
All right.
Is this your first game?